Welcome out there. We are on Learn Extra exam revision for physical science. Today we are looking at rates and chemical equilibrium. And the first thing that I want us to have a look at is the things that are important for this section as we go into our exam. So now, if you can look on the screen, things that are important are things such as you should be able to actually explain what a reaction rate is and also look at the factors that affect the rate of a reaction. By factors, I mean to say you must know that your temperature affect your rate of reaction, the concentration affect the rate of a reaction, the surface area, and surface area is for solids, affect the rate of a reaction. The other very important thing is your nature of reactants. Nature of reactants affect the rate of your reaction, and of course, a catalyst affect the rate of a reaction. Now, the other very important thing that you should know, you should be able to use collision theory to explain how various factors affect the rate of a reaction. Now, by so saying, I mean to say that when you look at the collision theory, it helps you explain how, for an example, temperature affect the rate of reaction. In other words, you look at the increase in kinetic energy of particles and how that will affect the number of collisions. The other very important thing that you should note is to sketch and interpret the graphs that has to do with change in energy. The reaction coordinates a graph in there, the effect of changing the rate of reaction. That is when you look at the concentration changes during a reaction rate, and as well as the energy distribution of molecules. We also call this graph the Boltzmann distribution curves. You should be able to sketch those and interpret what do they mean. Now, the other very important thing is to look at what a catalyst, how does a catalyst affect the rate of your reaction, and that is very important. Now, the other very important part of reaction rate is reaction equilibrium. Now, in reaction equilibrium, things that are important, you should understand what do we mean by an open system? What do we mean by a closed system? What is it that we mean when we say a reaction is reversible? At what state do we really say a reaction has reached a state of being in dynamic equilibrium? And you should also be able to list and understand factors that influence the position of equilibrium. We mean by factors such as temperature, factors such as pressure, and as well as concentration. You should be able to actually understand how do they affect the position of equilibrium. And very important, we should also be able to write down the equilibrium expression. In other words, the equilibrium constant expression, what we call the Kc. It's very important that when you are given a reaction equation, you should be able to come up with that expression. And the other very important thing, you should be able to calculate your Kc value. In other words, do calculations and also know what does this Kc mean in relation to the amount or the concentration of reactants and the concentrations of the product. Very important. You should be able to state and use Le Chatelier's principle. That is very important as well. The other aspect that you should be able to understand is how do we then apply these equilibrium principles in important industrial processes. Processes such as the Haber process for the production of ammonia, the contact process for the production of sulfuric acid, as well as the Ostwald process, which is for the production of nitric acid. And you should also be able to sketch and interpret the graph that shows the rate of reaction rate of reaction in a closed system, and also the change in concentrations of the amount of reactants and the amount of products. Now let's just quickly go and look at one of the questions that was set for reaction rate. Now this is a question that was adapted. You look at your screen, a question that was adapted from the DBE February 2014 question. Then the question reads as follows. They say the graph below shows the decomposition of gas P according to the following equation. There you have got it. You have got P, which is a gas, giving you 2Q, which is a gas, plus R, which is a gas, and delta H is less than 0 for that reaction. And then there you can see, there you have got a graph, and it starts at somewhere above 0.25 mole per dm cubed in concentration. It ran for 50 seconds in that fashion. And then the first question, they say, define the term rate of reaction in words by referring to the graph. Now, if we have to define reaction rate looking at this graph, you can go there and say, we are saying that the rate at which concentration of P is changing. By the way, note that it's okay even if we don't have that square brackets over there, because these square brackets actually means concentration. So we can just basically put P over there. So that's the rate at which the concentration of P is changing. That you would have defined your reaction rate in there. And then let's look at the next question, which is question number 2. They say, at which time, 10 seconds or 30 seconds, does the decomposition take place at the higher rate? And they say, refer to the graph to give a reason for the answer. Now, if you look back at your graph, at which time between 10, look at 10 over there, and also look at 30 over there. At which time between these two times is the rate of decomposition of P the fastest? Now, you can look at the slope of this graph. Now, when you look at the slope of this graph at 10 is greater than the one at 30. In other words, here, the slope is much greater than there. So in other words, you would rather say, for this, you will say at 10 seconds. At 10 seconds, that's wherein the decomposition of P was the fastest or was higher. And then what is the reason? Now, you will say the slope of the graph at 10 seconds is greater. Okay, now let's move on to the next question. Now the next question looks at, they say here, write down the initial concentration of P. In other words, at the beginning, what was the concentration of P? Now, if you go back and look at the graph over there, now you can check it's 0.25 now. The graph starts at a point which is higher than 0.25. Now, these blocks here, two of them means that's a unit. If you look at it tentative very carefully over there, so we'll look at it, so that will be 0.26, that will be 0.27. Now, our answer for this one will say, oh, it was at 0.27 mole per dm cube. In other words, that's the concentration initially of P. Now let's move on to the next question. Now, the next question, they say, the decomposition is carried out in a 2 decimeter cube container. Calculate the average rate in mole per second at which P is decomposed in the first 10 seconds. Let me just go back to that question. They say the decomposition is carried out in a 2 decimeter cube container. Calculate the average rate in mole per second at which P is decomposed in the first 10 seconds. Now, if we look at it, we are saying here that the first 10 seconds, in other words, from there to there. Now, what is the rate in mole per second that we have got? Now, if we look at it there, we'll go down and say, okay, let's go to it and say, our rate will be equals to, now look at it this way. We'll say the change in concentration of P divided by the change in time. Now, in this case, they want us specifically to express this in mole. Now, we should be able to look at our graph and say, okay, in our graph, how many number of moles do we have there? And how many number of moles do we have there? Now, let's first go and calculate the number of moles at the beginning and the number of moles at 10 seconds over there. So the number of moles at the beginning, so number of moles initially, number of moles is equals to concentration multiplied by volume. Now, what is our concentration initially? Our concentration initially is 0.27, as we have already said it above. So it's 0.27 multiplied by, what's our volume? Our volume is 2. So in other words, we'll say 0.27 multiplied by 2. 0.27 multiplied by 2. Let's look at 0.27 multiplied by 2 there. So we say 0.27 multiplied by 2. Our answer is 0.54. There we have got 0.54. That's 0.54 mole. That's initially. Now let's go down and say, now what is the number of moles that we had finally? What is the number of moles, the final number of moles in there? The final number of moles in there, how much is it? So we'll say that's concentration again multiplied by volume. Note that the volume that we have got didn't change. The volume that we have got didn't change. We still have 2 decimeter cubes. So what is the concentration of P at 10? Now, if we look at it very well, it's 0.15. That's the right concentration that we have got. So we'll say down there, that's the concentration is 0.15. 0.15 multiplied by 2. And then that will, as we go down there, we'll say, let's look at how much will that be. 0.15 multiplied by 2. What's our answer there? So that's 0.3. 0.3 mole. That's the answer that we have got in there. So going forward, we'll say, now the rate is equals to the change in concentration. Now when we say the change in concentration, we'll look at what is the final concentration that we have got. The final one that we have got is comma 3. Now we'll say comma 3 less. What was the initial one that we got? Let's just go up there and say the initial one that we got. Let's just go a little bit back. The final one that we had is comma 3. The initial one is comma 5, 4. So that's comma 5, 4. And then that will be divided by our initial time was 0. Our final one was 10. So it's 10 minus 0. And then, so that will be equals to, so just going up a little bit. So comma 3 minus comma 5, 4. What's the difference in there? So we'll find that is comma 2, 4. Of course, which is negative. Now that will be comma 2, 4 divided by 10. And the answer that we have got there, let's just look at it. So it will be minus comma 0, 2, 4. That is in mole per second. Well, that's it for question number 1. We are just going to have an ad break for now, and we'll come back and answer some more questions. And thank you for watching once again. Welcome back from the ad break. We are continuing with answering questions. Now, the second question that we are going to have a look at is a question which looks at a chemical equilibrium, and that's question number 2. Now, let's look at what question number 2 has for us. Now, they say a small quantity of cobalt chloride, powder is dissolved in ethanol, resulting into a blue solution. When few drops of water are carefully added to the blue solution, the color changes to the light pink. The following equilibrium has been established. There you have got the equilibrium, you have got the blue color, and you have got the pink color of the cobalt complex in there. And they say to investigate some of the factors which affect equilibrium, the following experiments were performed. Experiment 1, they say a small quantity of concentrated hydrochloric acid is added to the solution. And the observation that we had is that the solution turns deep blue. And the second experiment, they say the beaker with the solution is cooled by means of immersing it in ice water. Okay? And then the observation that we had there is that the color of the solution changes to pink. Now let's look at the first question. The first question, they say, how was the equilibrium affected in the experiment 1? Now, in experiment 1, remember, that's where they say a small quantity of concentrated hydrochloric acid is added to the solution. Now, when you add hydrochloric acid in this solution, we say the solution turns deep blue. Now, in other words, when you look at your equation there, or the equation that we have got, if it turns deep blue, it means that we kind of have more of that which causes the deep blue color, which is the cobalt chloride solution. Now, in other words, the reaction which actually produces the cobalt chloride was favored. Now, the question here is saying, how was the equilibrium affected in experiment 1? So the reaction that produces cobalt chloride was favored. So in terms of equilibrium, we can say the reverse reaction was favored. And we can also say, okay, equilibrium shifted to the left side. In other words, it shifted to the side which produces cobalt chloride. And the second question in there, they say, explain your answer in 2.1 in terms of Licher-Tallia's principle. Now, in terms of Licher-Tallia's principle, we can say when HCl is added, the concentration of chloride ions is increased. And what does this do to our equilibrium? It affects the equilibrium, and when this happens, the equilibrium will shift in the direction that cancel the effect of the change. In other words, that minimize the effect of this change. So when we say when HCl is added, the chloride ions, the chloride ions are increased or is increased, and in terms of Licher-Tallia's principle, that will make the reverse reaction to proceed. It will proceed what? Faster. And that will make this whole solution to be what? To be blue. So let's just go back to it. When HCl is added, the concentration of chloride is increased. That will make the reverse reaction to proceed faster, and hence that will give us a deep blue solution, deep blue over there. So that's it. So let's move on to the next question. They say, from the results of experiment 2, determine the sign of delta H for this reaction. Now, if we look at it this way, in experiment 2, they say the beaker with the solution is cooled by immersing it in ice. And the observation that we had is that the color of the solution changes to pink. If we look at this, it changes to pink. Now, which reaction actually gives us the pink cobalt complex? The forward reaction actually gives us the pink cobalt complex in there. Now, it means that that forward reaction was favored. The forward reaction was favored. Now, in this question, they say, from the results of experiment 2, determine the sign of delta H. Now, the solution becomes pink when the beaker is cooled, and we favored the forward reaction. Now, the reaction which is favored by cooling the reaction mixture, it must be a reaction that is exothermic. In other words, that liberates energy. And for a reaction that is exothermic, the delta H is less than 0. Now, delta H is less than 0, which means that this reaction is what? Is exothermic. This reaction is exothermic here. So now let's move on to the next question, which will be our question number 3. Now, in question number 3, they say a fertilizer company produces ammonia on a large scale at a temperature of 450 degrees Celsius. The balanced equation below represents the reaction that takes place in a sealed container. We have got a reaction there, and then we have got delta H, which is less than 0. Remember, it means that this forward reaction here is actually an exothermic reaction. They say, to meet an increased demand for fertilizer, the management of the company instructs their engineer to make necessary adjustments to increase the yield of ammonia. And then furthermore, they said, in a trial run on a small scale in the laboratory, the engineer makes adjustments to the temperature, pressure, and concentration of the equilibrium mixture. And the graph below represents the results obtained. There we have got the graph that represents the changes that were made in the equilibrium. Now, question number 3.1, they say, identify the changes made to equilibrium mixture at each of the following times. Now, let's look at the times that are given. So 3.1.1, they say at time T1. Time T1 is this time here. This is our time T1. Now, what was made in time T1, or what changes did the engineers made in time T1? Now, in time T1, you can look at the concentration of nitrogen there. The concentration of nitrogen actually increased, and the concentration of hydrogen and ammonia actually, the effect which was there was not that much visible, but later on they then increased, the other one decreased. But the change that we can actually see in T1 is that obviously at T1 the concentration of nitrogen was increased. Now we can say at T1, that's for 3.1.1, at T1 the concentration of nitrogen was increased. Now, let's go to the next question. Question 3.1.2. So in 3.1.2, they say, what is the change that was made? Let's look at this graph again. 3.1.2, at T2, what is that change? Now, I must say here that, guys, when you see a change that will make all the reactants and the products to increase in terms of their concentration at that point or at that moment, the instantaneous increase or decrease in the concentration, this increase here, they are indicative of the fact that something was done to the volume, because remember the volume depends on the number of moles and in other words, the concentration depends on the number of moles and the volume. Now, in this case, the concentrations of nitrogen, ammonia, and hydrogen all increased at that point. Now, it means that something was changed. In this case, it will be pressure. How so? Because we realize that the increase in concentration means that there was something which was done to the volume. So here we have got an increase in pressure. Remember, an increase in pressure, what does it do to the volume? The volume decreases, and that increases the what? The concentration. Now, in this case, the concentration increased, the concentration increased, the concentration increased, and it will mean that the pressure there was increased. In other words, at time T2, we can say pressure of the system was what? Was increased. Let's go to 3.1.3. Now they say at time T3. Now look at time T3. Time T3 is this time over here. Now if you look at it, what has actually happened? We now have the concentration of hydrogen increasing, the concentration of nitrogen increasing. Remember, nitrogen and hydrogen are our what? Our reactants. If we look at this equation here, they are our reactants. These are our reactants. Now, if they increase, and then our products, in that case, which is ammonia, actually decreased. So, in other words, the reaction that is using ammonia actually got favored. and it is in turn producing what? It is in turn producing a nitrogen, and it is also producing what? Hydrogen. In other words, which reaction is actually producing hydrogen and nitrogen? Is our reverse reaction. So our reverse reaction was favored. Did we change the concentration of anything? No. Did we change the pressure? No. Of course, that must be the temperature change. Now, if you look at it, it means that if we change the temperature, in this case, because our forward reaction is exothermic, what we must have actually done, or what the engineers may have done, is that they may have increased the temperature. Look at it. The forward reaction here is exothermic. It means that our reverse reaction is what? Is endothermic. By increasing the temperature, we favor the endothermic reaction, which is our reverse reaction. So it means that in time T3, we have actually done what? We have increased the temperature. The temperature was what? Was increased. So that's it. So let's move on and now look at question number 3.2. Question number 3.2. They say in question number 3.2, at which of the above times did the change made to the reaction mixture lead to a higher yield of ammonia? Write down only time T1 and or time T2 and or time T3. Now, if we look at it, let's look at this graph. Time T1, what do we have in terms of ammonia? So when we made these changes here, the amount of ammonia actually increased. Look at time T2. Time T2 is this time here. Whatsoever changes that we made, the amount of ammonia actually increased. And then in time T3, what happens to the amount of ammonia? The amount of ammonia decreased. So we can safely say that in time T1, in other words, in T1 and T2, in T1 and T2, that's wherein we have got the amount of ammonia, or the yield of ammonia increasing. I hope you got that one. So it's very important for us to be able to interpret a graph. Look at the graph and be able to tell us what is it that is happening in terms of the different concentrations, it be of the reactants or the product. Now, that's it. We are going to just have an ad break, and thereafter we'll continue doing question number 3. Thanks once again for watching. Welcome back. We are continuing with our reaction rates, or rates and chemical equilibrium. We're just looking at some of the questions, and the last question that we looked at was question number 3. We are going to continue looking at question number 3, and we are going to look at question number 3.3. Now, question number 3.3 reads as follows. They say, the engineer now injects 5 mole of nitrogen and 5 mole of hydrogen into a 5 decimeter cube sealed empty container. And equilibrium is reached at 450 degrees Celsius. They say, upon analysis of the equilibrium mixture, he finds that the mass of ammonia is 20.4 grams. And they say, calculate the equilibrium constant, that is Kc, at 450 degrees Celsius. Now we have to calculate Kc in here. Now note that it is very important for us to look at what is it that we are given, And in order for us to determine what is it that we still require in order for us to calculate the Kc. Now, to just simplify what we have to do here, remember, we have to calculate Kc. Now, remember, Kc expression is also very important. Now, let's first write the Kc expression for the reaction that we have got. Now, we know that Kc, let's just write that one, Kc will be equals to the concentration of the products. Our product in this case is ammonia, that's NH3. And when we look at it here, it will be to the power of 2. So squared divided by the concentration of hydrogen. Now the concentration of hydrogen will be to the power of, look at it here, to the power of 3. So that's the concentration of hydrogen to the power of 3. And the concentration of nitrogen to the power of what? To the power of nothing. No, that's to the power of 1. So that's 1 there. So let's just put it here. So that's to the power of 1. So in essence, I'm saying we need the equilibrium concentration of ammonia. We need the equilibrium concentration of nitrogen. We need the equilibrium concentration of what? Of hydrogen. And look here, they said at equilibrium, we have got 20,4 grams of ammonium. Now, we are given the mass of ammonia. Now, let's just go and try to find the concentration of ammonia at equilibrium, and that will help us to actually calculate our Kc. So let's just go and look at that. We'll say the number of moles of ammonia, that's N for ammonia, is equals to, when we look at it here, we are given the mass, so that will be the mass of ammonia divided by the molar mass of ammonium. Now, if we look at it, the mass that we are given at equilibrium, we are told that is 20,4. So that's 20,4 divided by the molar formula mass of ammonia is how much? Is 17. Now that's 17 there, and that will be equals to, if we look at it there, let's just go and calculate that. We have got 20, that's 20,4 divided by 17. Now answer there is 1,2. So that's 1,2 mole. Now, this is our number of moles, or the number of moles of ammonia that is there at equilibrium. Now, to simplify our job, or to simplify this calculation, we have actually looked at, we can use the Rice diagram, or the box, or the simplified box that helps us to determine the concentration. Now let's look at it this way. So here we've got the Rice table, which helps us to calculate the equilibrium concentration so that we can determine the Kc value. So Rice, by that I'm saying the first row here will have the ratio. In other words, that's the ratio in our reaction equation. The I standing for the initial number of moles, and then the C in the third row standing for the change in the number of moles, and then the E standing for the equilibrium. In other words, in the fourth row, we'll have the equilibrium number of moles. And the last row that I've got here is the equilibrium concentration. In other words, that's our concentration at equilibrium. So that's what that stands for. And then we must note that the initial number of moles, in other words, that's measured in mole, and we are talking about the change in number of moles. And as we go down, equilibrium, number of mole. And then when we go down here, the concentration is in mole per what? Mole per dm cubed. And then remember, our reaction is actually nitrogen, that's N2 plus hydrogen giving us ammonia. Ammonia is NH3, and we actually have to put a 3 there. That's to balance this reaction equation, and we put a 2 there, and we also have to indicate the states in there. So that's gas, and that's gas as well. Now from here, the first row, we actually have to put in the ratio, so which are the, when you look at the coefficients. So for nitrogen, that will be 1, and then for hydrogen, that will be 3, and then for ammonia, that will be 2. And going forward, remember what we have got at equilibrium, the number of moles at equilibrium of what? Of ammonia is 1,2 moles. So we actually have to put 1,2 mole here. So at equilibrium, we have got 1,2 mole. So we've got 1,2 mole there. So let's just wipe that. So we'll say at equilibrium, we have got 1,2 moles. What is the change that happened? Of course, we have actually produced 1,2 mole of ammonia. So we can say at the beginning we had nothing for ammonia, and then hydrogen we were given 5 moles, and then nitrogen we were given 5. So let's proceed. So we had nothing of what? Of ammonia at the beginning. But however, at the equilibrium, we find that we got now what? 1,2. Now, how much was formed in that process? So obviously, you will realize that if you had nothing and now you have got 1,2, you actually formed 1,2. So this is the number of moles that was actually formed. That's in the change row. How do we then find the number of moles of nitrogen and that of hydrogen? Now, when you want the number of moles of hydrogen, what you're going to do, you're going to multiply 1,2 that you had by 3/2. So when you do that, when you say 1,2 multiplied by 3/2, what you're going to get is you're going to get 1,8. And then again, look at it this way. You take this coefficient here and it divide the coefficient of nitrogen. What is the coefficient in nitrogen? The coefficient is 1. So you take 2, you divide 1 by 2. What is it that we are going to have? So you're going to have 1/2 multiplied by 1,2. And 1/2 multiplied by 1,2, that's going to give you 0.6. Now, this is the change. In other words, for hydrogen, what has actually happened is that because it's the reactant, you have used 1,8 mole. And for nitrogen, because it's also a reactant, you have used 0.6 mole. And the question is, what is there at equilibrium now? If you had 5 mole at the beginning, and you actually used 0.6 mole, what is it that is left? So it's say 5, let's just use that way. So it's 5 rather. We'll say 5 less 0.6. And what you're going to get is 4,4. So you can actually come here and say, okay, I'm left with 4,4 at equilibrium. So that's 4,4 at equilibrium. And then if you had 5, and then you use 1,8, so the difference there will be 3,2. So at equilibrium, what we have got is 4,4 mole of that's nitrogen, and 3,2 mole of hydrogen, and 1,2 mole of ammonia. Now, remember we have to use the concentrations when we look at the Kc expression like I've written it above. So we are going to divide all this number of moles here by 5 decimeter cube. And if you use your calculator, well, we're going to say, for the first one here, we're going to say 4,4. If you divide 4,4 by 5, which is our volume, the answer that you're going to get is 0.88. So let's just put 0.88 there. So that's 0.88. So this is the equilibrium concentration for nitrogen. And then let's go again and look for the one of nitrogen. Remember, the number of moles for nitrogen is how much? Is 3,2. So what we are going to do is to say 3,2 divide by what? Divide by 5. Remember, 5 is our volume. And our answer that we got is that one there. So that's 0.61. So 0.6, let's just check again, is 0.64. And then we go again and look at ammonia. We have got 1,2 as the number of moles at equilibrium. 1,2 divided by 5. And the answer that we have got is 6/25, which is 0.24. So that's 0.24. Now that's great. So going forward, what you actually have to do is to write your correct Kc expression. In other words, we are going to say Kc, so Kc is equilibrium constant, thus equals to the concentration of the products. Our products in this case is ammonia, so that's NH3. And then the square brackets stand for the what? For the concentration. And then we squared over there. And then that's divided by the concentration of the reactants. Our reactant in this case is hydrogen. Hydrogen, that's H2. And that hydrogen then is indeed to the power of 3. And then concentration now of the other reactant is nitrogen. And then the nitrogen, the coefficient, remember, is 1. So even if you don't indicate that, it is okay. Now, going forward, we can say that is equals to, now, what is the equilibrium concentration of ammonia? Look at it. We have got 0.24. And we no longer use the what? The square brackets, because the square brackets represents what? Concentration. And then we'll say that's 0.24 squared. That's the coefficient on ammonia. And then divide by the concentration or the equilibrium concentration of hydrogen. Remember, let's just check how much is that. Yes, our concentration is 0.64. So we're going to write 0.64. So 0.64, that's our concentration of what? Of hydrogen at equilibrium. And that's to the power of 3, which is the coefficient for hydrogen. And for nitrogen, we have got the concentration of nitrogen there is 0.88. That's in brackets. And what is the coefficient in nitrogen? The coefficient is 1, although it's not necessary to actually indicate that. So let's use our calculator for this calculation. Let's just go. So we're going to say it's 0.24. So it's 0.24 squared. And then we're going to divide it by, so divided by, I'm going to just open the brackets and say 0.64. And I'm going to close that bracket and say that's cubed. And again, I'm going to open this bracket and say multiplied by that's 0.88, so 0.88. And I'm going to close that bracket and say, what's the answer in there? So what's the answer? So let's get that answer right. So it's 0.24, which 0.2496. So we can safely say that's equals to 0.25. So that's equals to 0.25. And that's the value for our equilibrium constant. And remember, the equilibrium constant does not have a unit. It's a unitless quantity as such. And one other very important thing as I conclude on this question, the Kc value tells you a lot about the relative amount of your reactants at equilibrium and your products at equilibrium. A Kc which is less than 1, it means that you have got more reactants than products, whereas a Kc which is greater than 1 tells you that you have got more products than your reactants at that particular equilibrium. Thanks very much. I hope you have enjoyed the lesson, and I hope that you are going to write your exams and you will be ready for such questions. Thanks very much once again.